And welcome back to my channel. Today we'll be talking about maximum independent set. A maximum independent set, we're going to be calling it MIS for short. In the graph, is a subset of all the vertices of maximum size such that no pair of these vertices in the subset are connected through an edge. Let's grab a quick example. So let's say we have 1 being the root node, we have 2, 3, the children of 1, and we have, let's say, 4, 5, 6, and then here we have 7. We are looking for a maximum independent set. That is a set of vertices in which no pair are connected by an edge. So that means if we choose 2 and 3, we cannot choose 1, we cannot choose 4, 5, 6, 7, because 1 is connected to 2 and 3, 4, 5, 6 connected to 2, 7 is connected to 3. If we chose that independent set of 2 and 3, we would have, the size would be only 2 vertices. But if we chose, let's say we chose 1, we won't be able to choose 2 and 3. But then that means we can choose 4, 5, 6, 7. And if this is the maximum number of vertices we can get from this tree, who are not connected, or which are not connected by any edge, it means that this is the maximum independent set. Let's grab a further example. So let's say we have this example. Let's say we wiped this, and we had, let's say we have this. What would our maximum independent set be? So here we see that if we chose 2, 3, we can choose 1 and 4, right? So let's say we also have 5 here. If we chose 2, 3, we can't choose 1 and we can't choose 4, 5. But we see that if we choose 4, 5, and 3, we can't choose 1 and 2. But 4, 5, and 3 has a bigger size than choosing just 2, 3. So we could either go with 3, 4, 5, or we can go with 1, 4, 5. In this case, we have 2 choices of maximum independent sets. Either we go with 1, 4, 5, or we go with 3, 4, 5. So having said that, it's important for us to note that when we solve for a maximum independent set, usually we would have a value passed into this bracket, and that value should be the roots of our tree. So in this case, let's call this root u, right? So this would be MIS, then in the brackets u, showing that u is the root of the tree. So we can express, let's say, a maximum independent set of u using the following substructure, this substructure. So we want to find the maximum independent set w, where w would be the grandchildren, as in this case, grandchildren w of u. So I want to find the maximum between this expression and this expression. So this would be the children w of u, and I'm going to explain this in just a minute. So we see that in this first example, I think I should, we see that in this first example, we were either going to choose 1 and the grandchildren. Let's say 1 is u, right? That's the root. So we're either going to choose 1, and if we choose 1, we skip its children, then we choose its grandchildren. And of course, if there were other nodes here, for example, it means that if we chose 1, we'll choose its grandchildren of u, then it means we'll have to skip whatever it is directly connected to the grandchildren and go to the other to the other level. Now, that's what this expression says. This first expression says. But if we do not start from U or 1, as the case may be, would start from 2 and 3. And 2 and 3 would be the children, W. They are the children of U. So that's simply what this expression is saying. When we are looking for the maximum independent set, we can use this substructure to find it. So the first one says we want to find the maximum between these two substructures. We want to find, you just want to check whether starting from the roots and then skipping to the grandchildren, what the size would be. Then you compare that with starting from the children, right, and skipping the grandchildren. So that's basically what the maximum independent set says. Let's do one more computation before we end this video. So in this next computation, I have given you this, we've talked about the substructure. In this next computation, let us quickly look at how to use dynamic programming to calculate or to check maximum independent set. Let's start from this diagram. This is 1, which is the root in this case. We have 2, we have 3. Then from 2, we have nodes 4, 5, 6. And from 3, we have node 7 and node 8. Then from 4, let's say we have node 10 and node 9. And from 5, let's say we have node 12 and node 11. So we want to use a table to calculate or to keep track of what our maximum independent set should be. So the values that we would enter in this table will be the size of the maximum independent set. And that means that we want to select the maximum size and its corresponding vertices. So let's start. We're going to start from the lowest level. That would be the leaf nodes. So let's start from 9. At node 9, we have just 1. Let's just count. That's just 1 vertex. At node 10, we have just 1 vertex. We'll do the same for all of the leaf nodes. At node 11, we have just 1 vertex. At node 12, we have just 1 vertex. So now we are going to go, let's go with node 9. Node 9 and 10, we have that would be 2. Let's go with 11, 12. 11, 12, that would be 2 again. So we are done with everything on this level. So let's go to 6. We are calculating from the leaf nodes. And if you looked at this drawing carefully, this is not the best anyway, but if you looked at this drawing carefully, 9, 10, 11, 12, 6, 7, 8 are the leaf nodes. So let's go again. If we grabbed node 6, that's just 1. Node 7, that's just 1. 8, that's just 1. So let's say we grabbed nodes 9, 10, 11, 12. So if we grabbed node 9, 10, 11, 12, it means we would have nothing to do with 4 and 5. So we can go with 9, 10, 11, 12, and then 2. So here we have 9, 10, 11, 12. We would skip their direct parent, and then we go to 2, right? And this would be 5 nodes or 5 vertices. as the case may be. And if we used 5, 10, 11, 12, and then 2, it means for this, we can no longer count 1, which is the root node, and we can no longer count 4 and 5. So let's go to 7 and 8. Let's say we grab both 7 and 8. We have 2 vertices, right? And we see that if we grabbed, let's say this, if we grabbed, let's say we started from the roots now. If we went 1, 9, 10, 11, 12, 6, 7, 8, 9. Let's quickly write that down. Let's say we went from everything on the leaf node, 9, 10, 11, 12, 6, 7, 8, 9. Yeah. And oh, we already took 9. 6, 7, 8. That's everything on the leaf node. It means we can no longer grab 4 and 5 because they are connected to 9, 10, 11, 12. And we can no longer grab 3 and 2 because they are connected to 6, 7, 8. But it means we can grab 1, right? And if we grabbed 1, we would have 1, 2, 3, 4, 5, 6, 7, 8. We would have 8 vertices. Let's look at it critically. So it means of all the combinations of nodes that do not share vertices that I found, or that we found on this tree, we found this set of nodes of size 8, and it's the maximum number of nodes or maximum number of vertices in this tree that do not share any edge. So this is a maximum independent set. These nodes, they are maximum independent sets, and each size is 8. So we are going to end this video here. On our next video, or in our next video, we are going to grab solve one example using maximum independent sets and dynamic programming. I would see you on the next one.